guys, here is practice problem 7.1.1, and we're gonna go over this briefly. I'll put this. I think I already have this notebook up on Math on iLearn, so you can check the notebook out as well as this video. The problem here it gives us this diagram that has a pinned joint here at A and a roller support at B. And what that means is that at A, there's going to be an X and a Y reaction force, while at B, there's only going to be a normal force reaction, which in this case, since it's on a flat surface, is going to be totally in the Y direction. So we only have one direction we have to worry about there. And then we also have F1 and F2 that are applied at this point C, this pin joint. So this is our first introduction to trusses, and what it wants us to do is it wants us to find the force in each member of the truss. And so we have AC, CB, and AB that are all members of the truss, the different parts of the truss. And it gives us these things. It says that force 1 is 15 pounds, force 2 is 15 pounds, L is 10 feet long, and theta here and here are 30 degrees each. And what it wants, it doesn't just want the force in each of those, also wants to know whether that force is tension or compression, if I'm squishing or stretching each member of the truss. So to get started on that, I'll make this bigger so it's easier to see. I put in everything that was given. Force 1, I need to change this from previous version of the same problem. L is actually 10 feet, and theta is still 30. Cool. All right, so there are two basic steps to follow when you're doing truss problems. First, you've got to figure out what all the forces are for the entire truss system. So we're going to take this thing as a whole. We're going to take this whole ABC system and say, what are the forces acting on this, and balance them. We'll do the same thing that we've always done. Sum the forces in the X, sum the forces in the Y, and do summation of moments about points as we need to be able to figure out all our unknowns. Then after that, step 2 is going to be taking each joint, so point A, point B, point C, as necessary to figure out what the forces are at those points and find all the reactions there to solve for the unknowns, so that then we can draw a diagram and say, okay, AC is either in tension or in compression. Same for CB and same for AB. So those are our two basic steps. We'll take the thing as a whole, and then we'll take it joint by joint after that. So step 1, taking the thing as a whole, we want to sum the forces in the X and in the Y, and then we want to also do moments as necessary. So the first thing we'll do is we'll take the forces in the X direction and sum those. And that's pretty easy in this case because we have a force at A in the X direction. We also have force 1, and that's it, because force B doesn't have an X force. So that's solved pretty easily. The force at A in the X direction is just the opposite and equal of F1. So that's done. I'll shift enter on these so we can keep solving through. Now in the Y direction, we've got force at point A in the Y, and we've also got F2 coming down, so it's negative. We also have FB, which is pointed up. Now here we have two unknowns, so we're going to need more equations. We need at least one more equation to be able to figure out what those two are. So the first thing, what occurred to me first, was to take the moments about point A, because then we won't have to deal with the X and the Y forces at A. We can just focus on these other forces, and that would be easier. So to do that, one thing we're going to need to know is what this distance is. I call it CL, the vertical distance between point C and this component L down here. To get that, I did 4, which, well, and it shouldn't be 4, it should be, I should have just done, to get that fraction, you hit control and then /. So L divided by 2. And that'll give us the half the length of L. And then we multiply that by the tangent of theta. And we get 3.5. Okay. So now we're going to take the moments about MA. And the reason we wanted to find CL is because we're going to have a moment arm that depends on that F1 is going to create a negative moment about point A, and the moment arm for that is this distance between C and L. So that's why we needed that. So we're going to, so yeah, we've got a negative moment with F1 and CL, and we've also got a negative moment from F2 and half the length of L, and then we've got the force at B going up, and that's going to cause a positive moment because it's going the opposite direction. It's if I've got my thumb stuck out at my face, my right hand, and I take my thumb and stick it out at my face at point A, and I curl my fingers, that's a positive moment, and that's the direction that the force at B is trying to turn things. So now I have my moment, and I've got FB in there. Now I have two equations, and so I can solve and get FA, Y, and FB out of it. So I'll set up my solve equation down here, and when I have multiple equations, the way I set it up is I put a curly brace inside the solve equation, and then a comma between there, and then what I want it to solve for, the multiple variables I want it to solve for. So summation time, the sum of the forces in the y direction, remember the double equal sign, 0. Sum of the moments about A, I need to shift down around that, there we go. Double equal sign for 0, and then FAY and FB are what we're solving for. And I'll hit that, it updates. My force in the Y is that, my force in the B is that, cool. So then, because it doesn't automatically assign those variables that, I have to set it out here. So I'll type those in. Now we're going to start part 2. So that was part 1, figuring out all the forces in ABC as a whole. Now I'm going to take each joint. So you have to, there's a good example of how to do this in your book. In my book, it's on page 268. Depending on your edition, that might be different. It's example 6.1. So example 6.1, and then I like how it walks through it. There's, at the very bottom of the page, I'll post actually I think I have it here. I got it up for you. So this is what the diagram that we're trying to eventually come up with will look a little bit like. Obviously, it's not the same setup with the trusses, but they're different trusses, but that's fine. What we want to know is that we have to find a diagram that looks like this part right here, one that looks kind of like this, one that looks kind of like this, and then we can redraw this whole diagram, and we can draw all these arrows and figure out what's in tension and what's in compression. So that's kind of what we're shooting for in the big picture. So let's start at joint A and draw our figure there. So if we draw just a point on a piece of paper for point A, then we're going to have a force in the X, a force in the Y, and we're going to have a force in the direction of AB, and we're going to have a force in the direction of AC. And I like what Brother Miller says in his videos to draw the forces that are applied or that are reactions, so like force AX and force AY, draw those away always from your members, so your little diagram is going to look a little bit, you're going to have a force in the X going to the left, a force in the Y going up, and then force AC, and then force AB. Then we need to sum forces at that point. So I said sum of the forces at point A in the Y direction, and sum of the forces at point A in the X direction, and then sum all those up, and then I just solved for it by hand and set it equal to itself here so that I could get that out. And what that does, it tells us, okay, this is the force in member AC. And then I can do the same thing about in the X direction, since this one was in the Y direction, and solve for it. And I get the force in AB equal to 22.54. So I have force in AB, force in AC, and then we can move on to point B and do the same thing there and draw the free body diagram. Again, remember at point B, I only have one external force and two reactions, or they're not reactions even, they're just the forces in the components or the members there. So in member CB and member AB, plus the reaction force due to the roller. So in the X direction, it's pretty easy because it's just going to be from the members from AB and from a component of CB. And so I get the force in the BC, and that's actually the last one that I needed, because now I have my force in AC. I also have, that's right here. And I also have force in AB right here. And by the way, ignore this -10, that's from a previous set of calculations. And now I have force in BC. But the question now is, what direction, or what, are they in compression or are they in tension? So the way we figure that out is by drawing the diagram. I don't know if there's a better way than just drawing the diagram to figure it out. So if you've drawn your free body diagrams of each of those points of A and B and C, and you can use the negative signs or the positive signs, like for force AC, -9.2, that means that the force is going down this way at point A. So this is where it gets a little bit confusing, and I really suggest looking at the book to get their diagram and the way they explain how to do it. Because if you look at just, let me see if I can annotate this to make it a little easier to explain. If I look at just this part right here, just point A, that's what I just found. When I went around and did point A, point B, and point C, I found the forces acting on that point. Now, the forces in each member are going to be equal and opposite to what I found. So where I found up here in point A, that the force in AC is -9.2, then the force when I draw it on here in the member is going to be in the opposite direction. So really pay attention to the example, and also to the wording on here where it says use positive values to indicate tension and negative values to indicate compression, because it's all about convention here. You can think about it differently, but just pay attention to how they ask you to put it in. So yeah, when I drew it all out and got it, it turns out that AB is, let me check my notes. AB is in tension, BC is in compression, and AC is also in compression. And you can check your diagram and make sure on that, but that's what it ended up looking like. So go ahead and pop those in, and if you have any questions, comment below and I can post more sketches or things to help with that. Thanks.